We've covered make or buy decisions, parts lists, bills of materials, route sheets, and process selection. This week, we complete the process design picture and move into schedule design, the phase that directly answers how many machines you need, how many shifts, and how many people, and how big the building has to be. We'll also cover Pareto's law, a surprisingly powerful tool for deciding where to focus your facility design effort, and scrap estimation, which is where production planning meets real manufacturing math. Here's the full process design procedure. We've already completed make or buy list, parts list, bill of materials, process selections, and route sheet. This week, we finished the remaining three output documents, the assembly chart, operation process chart, and precedence diagram, and then move into schedule design. Think of this as a last mile of process design before we can actually start sizing the facility. The assembly chart shows how components are combined into the final product. The key building one is at the start to the end, the finished product, and trace the disassembly backward to basic components. The reverse that sequence to get your assembly order. Using the regulator example, we start with the finished product. The first disassembly step is unpacking. Then we remove the pipe plug. Uh, then the lock nut. Then we disassemble the body assembly, sub-assembly, and finally separate the body itself. On the chart, circle symbols represent assembly operations and square symbols represent inspection points. The assembly chart tells you what joins what, but it doesn't tell you anything about how each part was made. Here's the problem. Route sheets tell you how each part is made, the operations, machines, and times. Assembly charts tell you how the parts are combined, but neither one gives you the full picture of what's happening inside the facility. The operation process chart solves this by superimposing the route sheets onto the assembly chart. The result is a single document that shows the complete flow from raw material to finished product. There's two rules. If a component is purchased, it feeds into the chart horizontally. If it's manufactured in-house, it feeds vertically, with all its production operations shown above it. An even more detailed version in flow process charts, which adds transportation steps, storage delays, and shortages, including time and distance data. That's used for detailed layout analysis. The assembly chart and operations process chart are both special cases of a more general model called the precedence diagram. It's a directed network that shows which operations must be complete before others can begin. You've probably seen precedence diagrams before. CPM networks and PERT charts are both types of precedence diagrams. In the context of process design, the precedence diagram handles cases where there are multiple valid ways to assemble or disassemble a product. The assembly chart assumes one fixed sequence. The precedent diagram captures the full range of valid orderings. Here's a quick comparison. Assembly charts answers what joins what. Operation process charts answer how does everything flow through the facility. Precedence diagrams answers what must happen before what. You need all three, and they complement each other. Here is schedule design and the three questions. Schedule design is where we move from how do we make it to how much, when, and for how long. It provides answers for three fundamental questions: how much to produce, lot size decisions; when to produce, production scheduling; and feedback from marketing. How long will we be producing this product at all? That third question is critical and often ignored in facility design. A facility design for a product that will be discontinued in 2 years should look completely different from the ones designed for a product with a 10-year horizon. The first need flexibility, the second can justify specialization. The specificity of your demand information directly determines the quality of your facility plan. More specific inputs equal a more optimized facility. Vague inputs force you to build a more general purpose and less efficient facility. Three scenarios to understand this. First, a facility making 10,000 TVs per month versus one making 1,000 per month, obviously different sizes, but also different automation levels, handling systems, and workforce structures. Second, 10,000 TVs per month growing 10% is not the same as 10,000 per month flat. The first requires expansion capacity built in from day one. The second doesn't. Third, 10,000 per month for 10 years versus 10,000 per month for 3 months. With an unknown product after that, the 10-year horizon justifies a specialized, highly efficient facility. 3 months with uncertainty demands flexibility, which means higher costs per unit but lower stranded asset risk. The minimum market information table shows volume by product across year 1, 2, 5, and 10. Notice product B goes to 0 by year 10, being phased out. Product D starts at 0 and then ramps up. This tells us the facility planner that product B equipment should not be permanently installed, and product D capacity needs to be planned for future expansion. Pareto's Law. Pareto observed that 85% of the world's wealth is held by 15% of the people. The same pattern applies in manufacturing when surprisingly regularity. 85% of production volume typically comes from 15% of the production line. The volume variety chart makes the visual. Sort your products from highest to lowest volume and then plot them. You'll see a steep drop. A few products dominate, then a long tail of low volume items. The steep part is your mass production area. High volume, low variety, justifies dedicated specialized equipment. The tail is your job shop. Low volume, high variety, needs flexible general purpose equipment. The practical implication for facility design. Focus your layout and equipment investment on the top 15%. Get that right, and you've addressed 85% of your production volume efficiently. One important caveat. Pareto's law doesn't always apply. If your volume variety chart is flat, all products have roughly similar volumes. A general job shop facility is the right design for an entire operation. Don't force a Pareto implementation on flat data. Process requirements covers 6 calculation topics. Production requirements with scrap, production requirements with rework, the reject allowance problem, number of machines required, total machine requirement specification, and the machine assignment problem. Today we focus on the first and the most fundamental, scrap estimation. The others build on this foundation and we'll cover them in the next video when we go to GAM's optimization model for make or buy decisions. Scrap is a material waste generated during manufacturing. It comes in two forms. Geometric scrap is unavoidable. It results from shape mismatch, like cutting circular components from a rectangular steel plate. The corners are wasted by definition. Quality scrap is caused by process errors, machining mistakes, assembly defects. This can be reduced through automation, looser tolerances, and more certified suppliers. The key formula. Let PK, right here, let PK be the scrap rate operation K. The percentage of the inputs that become scrap, OK, is desired output of the units of goods. The critical insight. Because scrap compounds across operations, you always need more inputs than your market demand. And because scrap compounds multiplicatively, the order of operations matters less than the total scrap across the chain. Let's work through the example from this slide. A product has a market demand of 97,000 components. It requires 3 operations: turning, with P1 is equal to 4%, milling, P equaling 1%, and drilling, P equaling 3%. How many units must we start at operation 1? We work backward from the end processes. Here you can see that to deliver 90,000 good units to the market, we need to start at 105, 219,000 units at turning. That's 8,219 extra units at 8.5% overhead, purely to account for scrap across the 3 operations. For facility planning, this matters enormously. Every machine must be sized for not market demand, but production input. The turning machine must handle 105,000 units, not 97,000. All right, let's close out. Next video, we cover GAM's make-or-buy optimization model, where we put all of this into a real production planning optimization problem with machine capacity constraints. Thank you for listening. See you next video.